Hi guys, Assalamu alaikum. This is Arif. In this video, we are going to see how we can use functions inside our system Verilog and VHDL programs. And first, we are going to do that in system Verilog program and then in a VHDL program. So this is our system Verilog program first, and here we have defined a module project, and it has actually two inputs, which are clock and PC, and then there are four outputs which are going to represent our ALU logic, load logic, store instruction logic, and branch logic. So our PC is going to have 11 bits, clock is going to have 1 bit, and these are as inputs, and then we have outputs. We have defined those as reg as well, and these are our outputs. Now we can go to our main program, which is usually in this always block, and we are going to say at positive clock. What we are going to do, we are going to begin it. Then we have defined two local variables, which are f, which is reg, and then we have int variable as well, a variable of time int. And then we are going to first put our PC values, which are going to be bits. We are going to change those using equal sign and putting those inside this int variable, which is of type integer, and then we are going to compare those in our instruction cache. We can say that from the addresses 0 to 500 we have ALU jump instructions. I am just assuming this thing, and in that cache from 504 to 600 we have load type instructions. Then from 604 to 700 we have store type instructions, and then we have branch instructions on the addresses which are above 700, right? So we are going to say that if we get a instruction of ALU jump type, we are going to say implement this ALU logic. Then we are going to say we are going to get our instructions from these addresses. Load logic we are going to implement, store logic, and branch logic. So this is actually our complete program. Let's first try to run this, and then I am going to show you how we can implement this program using a function. Let me just show you Testbench quickly as well. So this is our Testbench. So this is the name of our Testbench module. We are going to give the variables clock and PC, which are our inputs, as reg, and then we are going to define our outputs with wire, and then we are going to call our main program, this project, and then we are going to use the same inputs and outputs here like this. And then in this initial block, first initial block, we are going to define our clock. This is the way we define our clock, and clock is going to have 20 nanoseconds total our time period. And then we have the second initial block, in which we are going to give inputs, and input is PC. So this is PC is equal to 1 address, this is PC is equal to 4, 8, this is 512 for load, this is 640 for store, just like we defined the ranges in our main program, and this is 704 above 700, which is for branch. So this is our complete program, and here we are going to end this. This is the end of the initial block, and this is the end of the main program. We have compiled it already. I am going to just show you first the output so that you can understand what kind of a program is this, its logic, and then we are going to implement that using the functions, because using the functions we can see the layout got changed. So let me reset it. These are our signals, inputs and outputs. We are going to drag those here. Then we are going to run this program. And now let's see our output so that you can understand. So this is actually our first instruction, right? So this is going to be ALU. This is 4 is also ALU, 8 is also ALU. All under the 500 are ALU branch. We are going to say implement these here, and we are going to say load is above 500, and then we are going to say store is above 604, and then we are going to say branch is above 704. So here these are going to change. Now let's end this simulation and try to implement the program with the help of the functions. So in order to use the functions, we can modify first of all code lines here in this program using the same logic. So we can comment out these lines and we can include these lines. So first of all, we can include these lines, which we are going to include in our so uncomment these lines function, and then we are going to say these are going to be our signal assignments. So what we are going to do, we are actually saying that we have defined an extra variable, this f, and this we are going to use now. We are going to say this is going to have 2 bits. We are going to say if the instruction is of type ALU or branch or ALU or jump. So what we are going to say, we are going to say f is going to be 0 0 0. This is going to be actually the output of our function. This is going to be the PC is going to be the input of our function. And now we are going to say like f is equal to 0 1 if it is of load type, f is equal to 1 0, store type, branch type, f is equal to 1 1. So we can use either assign here or without this one. Both are going to work. And then these f values we are going to use to give to our output. So we are going to say f is equal to 0 0, ALU logic, f is equal to 0 1, load logic, f is equal to 1 0, store, and then branch. So this is the way actually we can define our program, right? So this is going to work same way, but now what we can do is we can actually use these code lines which we have defined here in a function. So what we are going to do is actually I can actually comment out these lines and use these same code lines in a function. So these we are not going to change, whatever it is our output logic, right? But the above code lines we are going to use inside a function, and here you can see this is equal to and this one like this, but not here. If you are saying in a function, we can use something like this or this. Now the same code lines I am going to use inside this function. So let me remove these comments lines so that we can include these into our code. So what we are going to do here, we are going to define a function, and what we are going to say, we are going to name it as classify function. It is going to have our PC as inputs, right? So same way we are going to define the PC address as 11 bits, just like our input. and then we are going to define a reg which is going to be output of our function f, just like in the paint program I was showing you. Then this int variable like this, which is of type int, and then we are going to say okay, put whatever is we are getting the PC value in the bits and convert those into an integer like this, and then we are going to compare, and then we are going to say f is equal to 0 0, f is equal to 0 1 if it is ALU, if it is load, if it is store, and if this is branch, something like this. You can use either a sign or equal sign, right? And then in order to return our output variable, we can either use this line return f, or we are going to use this name of the function which is classify equal to f. Both of these lines are going to work the same way, but remember this thing, this is very important. Whatever is the type of this f, we are going to give this type here as well. You see this one, we can either use these bits or we can put a reg as well. This below line would function same way, although it doesn't have the reg, but if we are going to exclude this one, it is going to return only 1 bit value, not the 2 bits or 4 bits or 6 bits. If we are going to remove this part, so it is going to return only 1 bit value. So the program is going to compile, it is going to run as well, but the output logic is going to be different. So remember this thing. So now if we are going to call this function classify, which is going to get PC as our input, so we can call using these two ways. We can either say f is equal to this one, classify PC, PC is going to get the input values. This is going to be its argument, right? So rest of the program would be something like this. So let's save this program and try to compile and run this program, and we are going to see our output the same way. So let's drag our input and output signals to this window and run this program. You see, same inputs and outputs, same way we are going to enable these things: load, store, branch, and jump. So this is just one type of function which I have defined here, which is going to get our input bits, which are bits, and then we are going to get our output bits, which are bits as well. But it can be an integer as well. Like if we are going to define some adder, we can say integer, and then we can say a and b, and then we can say output is also going to be something like integer. We can type here int, but these are just like logical 0 and 1 bits. So let's now move over to our VHDL program and try to implement the same program in VHDL using a function. So we can close this previous program windows. So this is actually the main program of our VHDL program. So here we are going to give some libraries here. So since we are going to convert our bits into an integer, so we can use this library. In the Verilog, we can actually convert them directly using the equal sign, but here we are going to use a function convert integer, which is going to be from this library. That's why we are using this library as well. So same way, this is our program name entity, and then we are going to say entity is going to have two inputs, clock and PC. and PC is also going to here be of 11 bits, and then we have 4 outputs: ALU logic, load logic, store logic, branch logic. So this is our output. And then we are going to say in our architecture. So we are going to begin our architecture. We are going to say process clock, and then we are going to say this is our int variable, right? And this int variable we are going to use here. We are going to say convert the values of the PC into an integer, put those into this int. So after that we are going to say start the clock. If clock is equal to 1 and clock take event, then we are going to say, or we can use this line as well, both are going to work like same way. Then we are going to say, okay, if clock is between 0 to 500, it is going to be ALU or jump instruction, right? So ALU logic we are going to implement. These can be a lot of code lines, but I am just here defining like ALU logic. You guys know is something there, so I am going to use just one line. And then we are going to say, okay, if the PC between range 504 to 600, this is load instruction, implement load logic, store logic. And then we are going to say above 700, it is going to be the branch logic and if, right? So this is going to be our complete program, same program using the VHDL. And then we are going to say end clock, end process, and end behavioral. Now I am going to show you its test bench as well. This is this test bench. These are the two libraries. And then we are going to say that in this architecture of our test bench, we are going to use the main program as a component. So it is going to have same inputs and outputs, something like this. Then we are going to define those inputs and outputs using signals. This is clock, PC is input. These are all outputs. Then we are going to say begin. And then we are going to call this program, and we are going to use this port map, and same way we are going to give this clock signal, PC, and output signals. And then we are going to say process, the process block begin. This is the way we can define a clock in a VHDL program. This clock is same way 20 nanoseconds like in our system Verilog program. And in this second process begin, we are going to give our input PC value. This is PC is equal to 1. Jump type instruction, for example, is there. Then we are going to say after 49 nanoseconds change the value PC4. We can say some other instruction, like for example ALU add instruction is there, then 8 add I is there at 8. We are just assuming. Then we are going to say load word instruction is above 500, and this is 512 address. Then we are going to store word is at 640. This is this PC accordingly. Then we are going to say this is actually the branch instruction is at, for example, above 700, 704. So this is end process and behave. So this is actually our complete program, right? Now let's try to compile and run this program so that you guys can see the behavior of this program as well, which is going to be the same inputs and outputs. I have not changed the program so that it's easy to understand the main thing, and that is how to implement a function inside Verilog and VHDL, rather than understanding what our program is doing. So these are all input and output signals. Drag those. Now we are going to see, we can see the same. This is actually our ALU instructions and ALU logic. This is our load logic. This is our load instruction. This is our store instruction. And this is our branch instruction at this address. Same inputs and outputs. But let's now go and run this program using a function as well. So go to main program and comment out these lines. Instead of getting the output values directly, we are going to use these inside a function. So include actually these code lines, we can say same way actually, you know. These are the code lines actually we are going to use inside a function, but first I am going to show you here. This way this is going to also run, like we are going to say that input of our function is going to be PC values, output is going to be this f is equal to 0 if it is ALU instruction, f is equal to 0 1 if it is a load, if f is equal to 1 0 if it is a store, f is equal to 1 1 if it is going to be a branch instruction, right? And then we are going to say we are going to come here and then we are going to say include these lines. Right, so we are going to say if as f is equal to 0 0 implement ALU logic, if f is equal to 0 1 implement load logic, if f is equal to 1 0 store logic, if else then branch logic above 700. So this is going to save a compile and run, but instead of using these things here, this is the way I just wanted to show you. These code lines actually we can include inside our function. So let's comment out these lines and use the same code lines in our function so that we know in a VHDL program how a function is defined. So in this architecture block, we are going to actually define this function, declare and define both things. So here we are just declaring this function. Function is this again classify name. It is going to have a PC address. So it is going to, this variable PC address is going to have 11 bits. So what we are going to return? We are going to return this f variable. But inside a function, whatever other variables we are going to define, we are going to define same way under this s, not anywhere else. So return variable is going to be this one, but if we are going to use some other variable as well, which we are going to use this int, and then in this begin block, what we are going to do, we are going to use this convert integer function to convert the bits which we are getting from this PC address, and we are going to put those inside this int variable, because int is of type integer and these are vectors in bits. So we are going to convert those. So we are going to get the PC values in terms of integers, and then using this int variable, we are going to say if the PC address is from 0 to 500, ALU logic f is equal to 0 0. If PC between 504 to 600, load logic f is equal to 0 1, then 1 0, and then 1 1. And here we are going to end our if, and then here we are going to actually return f, you see, and here we are going to end our function classify. So you see function implementation is just a bit different. We are going to return function output like this. This is going to be our output, which we are going to return f, not this one, but this variable also we are going to define under this is, you see. So we are going to get bits as our inputs, bits 2 bits 0 to 1 as our outputs, but we can define this function using an int as well. If we have just an addition function, we can say okay, input is going to be, instead of this vector, a type of integer, output is also instead of a vector, we can say it is going to be of type integer, this integer. But here we are not going to do that because we are using bits here. And now in the main block, we are going to call this function here like this. We are going to say, again we have defined a local variable here f, You see, we have defined an int previously, but now we have defined actually a f variable here, which is of type vector 2 bits, and we are going to put whatever we are getting from this PCs. We are going to say, okay, if PC is between this range to this range, using this function, we are going to say f is going to be either 0 0 or 0 1 or 1 0 or 1 1, and then we are going to say using if block, if f is equal to 0 0, implement ALU logic, 0 1 load logic, store 1 0, and then else 1 1, f is equal to 1 1, branch logic. So we can say this is the way actually this is, we are here using this end if of our clock and then end process and then end behavioral. So now let's compile and run this program and see what we get using this function. So program is compiled and let's see our output. So we can see the same inputs and outputs, right? So ALU logic is turning 1 here due to these instructions. This is load instruction, it is load instruction, and then the same way. So now you guys have actually seen how we can implement a function inside a VHDL as well as a system Verilog program. But let me show you just one more thing. I think we have defined this variable like this here, right? But let me see if we can use or define this f variable outside this became as a signal, and program is going to work or not. So we can say exclude these code lines, comment out these lines, and outside this begin block we can actually define it as a signal, not inside this begin block. So we can say signal f is equal to this. Now if we are going to call this function, what we are going to do here, instead of using this like this, we can actually exclude this line and call this function like this. So exclude this line and call this function like this. So now I think this is going to work, but let's save this program. Compile this program and run this program. Drag these signals here and run this. No, actually we can see the output is different. So this is the way actually we can't implement it. You see, the first three inputs are same, but look at the way this branch instruction is going on. It is starting before even this. This is the way we have not given our test bench. So that means that we can't use something like this. So this is actually the wrong way. So we can say this is not the right way. We can't define f as a signal outside this block. We can define f as a variable inside this block. And then now if we are going to compile and run this program, we are going to see our correct output. But that I have already shown you through the simulation. So thank you guys. I hope you guys have enjoyed this video. Have fun.